Good morning, everybody, and welcome to week 3 of the CWS preparation course. Today we are going to be talking about the introduction to water chemistry. I'm going to go on and mute everybody here so that
I need to get one. I
don't get the background noise. There we go. So today we're going to be talking about the introduction to water chemistry, and let's get started. As always, I always like to say thank you before I start any presentation, and I never mean it any less each week. The one thing I do want you to know is how much I appreciate your time, and it's always my goal to make sure that the information that I give to you is at least as valuable as the time you're giving to me. It really does mean a lot to me that you're allowing me to serve you in this way, and that you're bettering yourself for this industry that I've come to love so much. So thank you very much. All right, so before we really jump into the whole chemistry thing, I kind of want to preface this a little bit and say that I think that the chemistry stuff is one of the biggest reasons people are deterred from taking these courses or from getting their certification. I remember, I mean, for me, I went to school to be for theater and speech and to teach high school theater and speech. It had nothing to do with chemistry at all. And I remember 15 years ago when I picked up the Water Treatment Fundamentals book and I started reading the chemistry stuff. Wow, we talk about brain explosion. I mean, the stuff is just so academic, and I could definitely see how it would be a deterrent. Some of it is kind of tough. And I think that way back then, the CWS exam was almost all chemistry. The thing that I can tell you about the exam now is that it's only 12%. Only 12% of the questions out of the 150 on the exam are chemistry questions. It's only 12% out of the, so that's roughly, what, 15, 16 questions that are going to be on chemistry. They're going to there's not a ton of effort spent on the chemistry stuff. I mean, if you looked at the curriculum, if you looked at the outline, which you can find on the web page, there's a link to the outline so that you know what's coming up each week and what to study for and what to read. You'll see that there are 2 weeks. There's this week and next week that are chemistry. And so, why 2 out of the 15 all specifically based on chemistry? And that's because, number one, I didn't want to shove it all into 1 week. It's brain dead. I mean, you guys would leave here being just completely unproductive the rest of the day, maybe because your brains were just hurt. And secondly, I think that it's really important that you understand the chemistry, even if you're not going to be tested on it a whole lot, because it is the basis of how so many other things in the water treatment industry work. So many other treatments, it's how they work. So that's the purpose of the 2 weeks in focused on chemistry here. Today, what we're going to talk about is a whole bunch of chemically stuff. So it's going to be like a, chemically thing. And, like compounds and mixtures and the anatomy of an atom, physical changes, and not the kind that make my 16-year-old uncomfortable. Chemical reactions, which is why stuff likes each other, and let's get right in on that physical and chemical change. Okay, this is important. You may see this again. This is kind of relevant. So, a physical change basically is when there is no change in the molecules. Okay, so you've got water is one of your best examples of that. When water comes in 3 forms, okay, and so do most matter is this way as well. Okay, it's going to come in 3 forms as well. But you've got ice, you've got liquid, and then you have vapor or steam. There's also a 4th stage called plasma, We're not going to talk about plasma. That gets way, way too advanced chemistry and for what we're going to talk about here. But we are talking about the 3 stages. So when you think about water, okay, let's just keep it simple here. Water it's ice, okay, and it's in its solid form. The molecules are there. They're just moving around a lot more slowly. They're still moving. Okay? The colder it is, the slower the molecules are moving around. But they're moving very slowly, but it's a solid. Okay? When you heat it up a little bit, the molecules start moving a little bit more. They start moving around a little bit more, and they turn into a liquid. And when you heat it up even more, then it turns to vapor or to steam. That is actually the case if you took a slab of steel, okay, just like steel, metal, that's in its frozen form. That metal, because it's hard, is in its frozen form. If you heated it up enough, it would become liquid. And then if you continued to heat it, if you could get it even hotter, then even that steel would become vapor. So that's the case with everything. But you're not changing the molecules in there. That's just a physical change. Okay, you're not changing any of the molecules. The molecules in water, they're still the same, H2O. So you've got 2 hydrogens, 1 oxygen. They're still the same. You have not changed them at all. Okay. Another example of a physical change, if you took a 2x4 and you cut that up, and if you had an 8-foot 2x4 and you cut it into 8 pieces of foot-long 2x4, you haven't changed anything except physically. All you've done is made a physical change. Okay, that's a physical change. Chemical change is when new molecules are formed as a result of the change. Okay, so when you think about it, fireworks are caused because the reason you get the explosions are because of the chemical changes that are occurring in rapid order. When you burn that 2x4, then you're making new molecules, frying an egg. Even rust on a sink, okay, you're forming new molecules. You're actually taking a chemical change. You're creating a chemical change when you go from Fe++ or clear water iron to oxidized iron. That's a chemical change because you're forming new molecules or new types of molecules. So let's talk about the periodic chart of the elements. I'm going to put my little drawing pin on here so we can, I know everybody's, look, it's art time with Kelly again. They always look forward to this, I think. So let's go. Okay, so Jen's making a comment here. You may be asked a question about the changes in burning a piece of wood or coal. That would be a chemical change. All right, so periodic chart of the elements. Now, I took chemistry in college and barely passed, and so I kind of remembered some of this stuff, but when you put it in terms of water treatment, it's actually kind of interesting. So there's a couple things about the periodic chart of the elements that I'm gonna point out to you. First off is the word elements. Okay, keep that in mind, elements, because when you're trying to remember what the smallest substance is, breakdown. Okay, 1 atom of an element is the smallest substance we know. Okay, so the lightest, smallest that is out there is a hydrogen. Now, a couple things about this periodic chart of the elements. Number one, usually things on the left-hand side are positively charged. Things on the right-hand side, closer to the right-hand side, are negatively charged, usually. Secondly, you've got when they ionize, that is, when they ionize. Secondly, you've got the way it goes, and the reason they have the breaks in it is that it goes lighter to heavier all the way down to the last one is heavier. So they go by atomic weight. So the lightest, the smallest is all the way, that's hydrogen up here, and they go all the way down to the heaviest. Okay, now the most relevant thing that you need to know is that anything in a vertical line with anything else carries similar chemical properties as it reacts similarly to anything else in that vertical line. So, for example, in the first line here, you'll see lithium, and that's the line that hydrogen's in. You notice sodium right here, Na, and potassium. Now we know actually that we can regenerate a water conditioner, a water softener with sodium or potassium. The reason that works is because potassium and sodium, they're both in that same vertical line. So you could theoretically use pretty much anything else in the same vertical line to regenerate that softener, including hydrogen, which is what is used when you're using a deionization system. So when you're using a deionizer and you're regenerating that, then you regenerate it with a solution that has a lot of hydrogen in it, and that's what you regenerate it with. We'll talk about that again in the future. If you go over here to the alkaline earth metals, the yellow here, you'll notice that magnesium and calcium, both really close to each other in the same vertical line on the periodic chart of the elements. So they both react the same way. Now, this is important because this is why if you have things like barium in the water or radium, then if you have those things in the water, then they're going to fight with the magnesium and calcium for room on that resin bed, on the resin bead. So those things you have to take those things into account if you have those in the water, because it will exhaust that resin bed. If you go over here, you'll also see chloride or chlorine. It's chlorine here, becomes chloride when it becomes ionized. And then we are going to talk about the noble gases at some point too. Okay, these guys right over here. And I just want to show you where they are, okay, because we're going to refer back to them here in a little bit. But that's the biggest thing that you should understand or know about the periodic chart of the element. Kind of interesting, just in the way they react and why they stick to different things. Okay, so matter, like I said, all matter comes in a solid, liquid, or gas form. Also plasma, but we're ignoring plasma for the purpose of this class. Okay, if you can break that down through your little organizational chart here. On one side, you're going to have mixtures, and on the other side, you're going to have pure substances. Okay, so let's go with mixtures first. Mixtures come in two different types. You've got the heterogeneous mixture and the homogeneous mixture, and then you've got over here for the pure substances, elements. Remember, periodic chart of the elements, and then compounds, and we'll talk about those in the next couple slides. But a couple things to remember here. An atom is the smallest possible unit of an element. Okay, so when you're looking at that periodic chart of the elements, one hydrogen, so it's one atom of the hydrogen element is the smallest possible unit. So an atom is the smallest possible unit. A molecule is when you take two or more atoms and you put them together. So so a hydrogen molecule could be two hydrogen atoms put together. Okay, but a molecule doesn't have to be the same substance. It could be something different. So it could be that you've got let's just, I don't know, just randomly throw something together. So maybe two hydrogens and one oxygen. That would make a water molecule. Okay, so it would form a molecule when you take two or more atoms of one or more elements and you put them together. So we're going to start here. We've got, so this would be hydrogen. Okay, you take a couple of those atoms and you throw them together. Here now you've combined molecules of a compound, so it becomes a compound when you actually take two or more of these elements and you put them together. That becomes a molecule of a compound. And when you start taking different kinds, that becomes a mixture. So now you have different mixtures or different compounds, different molecules mixed in a solution altogether. That becomes a mixture. All right, so go to the mixture side of this thing. On one side, you've got the heterogeneous mixture. Heterogeneous mixture is like a bowl of trail mix. Okay, that's where basically if you took a big, huge bowl of trail mix and you took one scoop out of one side of it and another scoop out of another side of it, then you may have different amounts of peanuts and M&Ms and cashews and raisins and all that stuff. It's going to be a different count. It's going to be a different makeup. It's going to be similar, but it's going to be a different makeup. So that's a heterogeneous mixture when it's not uniform all the way through. It could be different depending on where you take the sample. A homogeneous mixture is like the creepy Kool-Aid guy. Okay, it's like if you could close your eyes for a minute, imagine yourself being just a normal, everyday, average kid sitting in the school lunchroom, and boom, here comes this big, gigantic glass pitcher screaming, breaking through the concrete wall, and then, screaming, "Hey, Kool-Aid!" And you're like freaking out as a kid. You're like, ah, because you've been watching Creature Feature on TV and the Godzilla movies and everything, and they're all coming, and you're thinking that it's not Godzilla at all. It's really the Kool-Aid. Anyway, sorry, I forgot where I was here for a minute. Kool-Aid is a homogeneous mixture. They, wow, just brought me back to years of therapy. So it's a homogeneous mixture. A homogeneous mixture is when you've got this fluid, this liquid, and it's the same all the way through. So it doesn't matter where you take the sample of the Kool-Aid guy's, I don't know, is he sloshing around? How does that work anyway? I mean, I don't know. So if you took one sample of Kool-Aid from one side of the pitcher and another sample of Kool-Aid from the other side of the pitcher, the chemical makeup would be about the same all the way through. And so that's a homogeneous mixture. I mean, when you hear about homogeneous milk is basically they spin it until the fatty bubbles are equal all the way through. So the fat is dispersed all the way through that milk. That's homogenized milk. So that's a homogeneous mixture. Compounds, and we already talked about elements. Elements are the smallest, they're on the periodic chart of the elements. A compound is when you take a couple different elements and you put them together, and they have three defining characteristics. Every compound, you can tell it's a compound because it has three defining characteristics. Number one, it has a definite boiling and freezing point. Number two, it has well-defined characteristics of its own, different from its component elements. And an example of that would be, salt, table salt, like sodium chloride, right? So sodium by itself is this silver gas, it's a silverish metal, kind of looks like it has a kind of a sheen on it, almost like an oily sheen on it. And chloride is a greenish gas, but when you put them together, they form salt. They form this crystal salt. So they look completely different when you put them together than they do separately. And a compound is always homogeneous. So a compound is always going to be like the creepy Kool-Aid, oh yeah, guy. So, all right, are we having fun yet? Okay, so put on your thinking caps and let's really delve into the chemistry stuff. Ready? Okay. Okay. So let's start from the left and let's go all the way through this. No, I'm just kidding. We're not going to do all that. Too complicated. All right, so the anatomy of an atom. Let's go back there. There was something called a peptide is what that thing was, and I only know that because when I plagiarized the clip art image from Google Images, it said diagram of a peptide. So I don't know what a peptide is, but it looked like something fun and cool to do. So, okay, this is actually kind of cool, though, I think. Right, so everything in the universe, from the smallest to the biggest, it kind of has the same makeup, kind of has the same structure to it. And if you think about our solar system, you've got the sun in the center, and then the planets that surround the sun, and they just sort of move around, you know, around that. They orbit around that, around the sun. Now, the picture here, the diagram shows it as being a lateral orbit, and that's not always the case. When you look here down at this little picture of the atom, you know, these guys are moving around. They're moving around the different planes. That's a little closer, but it's not even really that way either. They're kind of zigzagging in and out and kind of moving all around it. But so it's not a uniform orbit, but it is an orbit. It is a lot like the planet. So we're going to keep it pretty basic as we're talking about this. But an atom works much the same way the solar system does. You've got the nucleus in the center, which is like the sun, okay? And then you've got the electrons that orbit on the outs around that nucleus. Wow, I can't talk. Nucleons, what the heck? The electrons orbit around that nucleus, and the electrons are sort of like the planet. So here, this is a hydrogen atom. So basically, you've got the sun right in the center. This, by the way, is where the protons are. The way I always remember that is I always think of the sun giving light and positive. You know, everybody feels good when the sun's shining. So that's positive or pro. So that's where the protons exist. The protons exist in the sun, in the center, and the sun's always in the center. So that's where the protons, it's a nucleus in the center, okay? Electrons are the planets. So if the protons are in the sun, they're in the center, then the electrons they orbit. They're what orbit, okay? An atom never loses or gains more protons. It always has the same amount because they stay right there in that sun, in the nucleus, okay? There's also something called neutrons, and neutrons, the only purpose neutrons serve are to add mass or to add weight. So they change the weight of an atom. They simply add mass. That's all they do. What changes the chemical properties of an atom, what does move kind of back and forth, and we're going to talk about this a little bit as we get into this, is the electrons. So an atom will give up or take electrons from other atoms, and that's how things are formed, is through the electron exchange or the planet exchange, planetary exchange. That sounds fun, planetary exchange. I think I've heard that on Star Trek somewhere. Okay, so that was a hydrogen. Now we can look at just a couple others, and this is a picture that came basically right out of the book. So, all right, so we know in this one that we have 7 protons in the center, 7 neutrons in the center, and we also happen, in nitrogen, we also happen to have 7 electrons. So there's different orbits, okay? And there is a calculation that allows you to figure and calculate what the most amount of orbits there can be, or electrons there can be in each orbit. You are not going to need to know how to do that. If you delve deeper into chemistry for some reason outside of the water treatment industry, then that's important to know. It becomes important to know. They do mention it in the book and talk about it, and I'm going to mention it in the webinar here, but you will not need to memorize the formulas to calculate how many electrons can be in each orbit. It's not something you're going to know. It's not something I have ever used in the water treatment industry. But if you look in the inner orbit here, the innermost orbit, we've got 2 electrons, and in the next one, there are 5 in the outer orbit here in nitrogen, so that gives a total of 7 electrons. If you have an atom different than an ion, okay, an atom always has the same amount of protons and electrons because it's neutral. An atom would be neutral. Okay, an atom would not carry an electrical charge. Now, the thing that's kind of confusing about that is the atoms do not exist in nature. So there's no such thing, and atoms are always ionized. So atoms are almost, well, they have to be created if they are, and they just don't exist in nature. They always give up or take an electron to or from something else. But an atom itself, if you're looking at the periodic chart of the elements, an atom itself would have the same amount of electrons and the same amount of protons. It would be completely neutral. Okay, and what I mean by neutral, protons carry a positive charge, electrons carry a negative charge, and so they sort of balance each other out. 7 protons and 7 electrons would mean that they're neutralized. They neutralize each other. Okay. Oxygen, you'll see you have 2 electrons in the inner orbit, 6 electrons in the outer orbit, and then that means they have 8 protons in the center. Now, they also happen to have 8 neutrons in the center, but that's not always, you don't always have to have the same amount of neutrons as you do protons and electrons. In fact, if you look down at sodium, sodium has 12 neutrons, but only 11 protons and 11 electrons. And also chlorine has 18 neutrons, 17 protons and 17 electrons. Okay, but you'll see also that you can go further. So sodium here, and I'm going to give you a little preview here. Sodium has only 1 electron in its outer orbit, but you see the sodium has 3 orbits, showing. So you've got 2, and then 8, and then 1 electron in its outer orbit. Chlorine has 2 in its inner orbit, 8 in the middle orbit, and it has 7 in the outer orbit. Okay. So here's that formula if you want to know it. Basically, to calculate what the maximum number of electrons you can have in an atom's orbits, you take n, where n is the number of the orbit, and you go 2n squared, so 2 times n squared, and that tells you how many electrons you could get. You can have. So we're not going to spend this. Not going to spend a lot of time on that because who cares? Okay, yeah, like Jen's saying, cool to know if you really want to feel smart and it's actually good to at least know that there is a calculation, that there is only a certain number of electrons that can go in each orbit, because if you are talking about, you know, if you do get into a conversation with somebody who understands chemistry, who understands all this stuff, then they're going to know it, and it does give you credibility out there in the field. I mean, it is part of the education. All right, so this is one of the coolest things about this whole chemistry thing that I think this is actually pretty cool. It did sort of put it all together for me. So the magic number is 8. Okay, 8 is the magic number. Everything is based on 8, on the number 8. Everything's happiest when it has 8 electrons in its outer shell. Closer to 8 electrons in their outer shell it is, the happier it is. Okay, so I think it's pretty cool. Actually, there's a book by Catherine Novell called B8 that I read a couple times, and it's based on chess, and it's all focused around 8. It's pretty cool on the number 8, because chess is all based on the number 8 too. Did I say the letter 8? I meant the number 8. If I said the letter 8, I'll have to go back and listen to the recording. Yeah, wow, I feel smart. It's kind of cool when you turn 8 on its side. It actually, you know, gives you the infinity symbol. So it's kind of interesting that it ties so closely together with the universe and how things work. All right, so why compounds form? This is basically it. So we've got oxygen, and we're going to look at oxygen here, and we know that oxygen has 8 protons and it has 8 electrons. So if we count them, we've got 2 electrons. So here, this isn't showing the nucleus, but the nucleus would be here. So around its orbit, you've got 2 electrons in the inner orbit and 6 electrons in its outer orbit. Now, we know that water is formed when you take 2 hydrogens and you combine it. The reason they do that is if you take this hydrogen with its one electron in its outer orbit and stick it in here, and this electron with its outer orbit, or this hydrogen with its electron in its outer orbit, and stick it over here, we have water. For some reason, I've heard people call this the Mickey Mouse ion. I don't know why exactly, but okay, we'll go with it. And so that forms water. Water is actually really, really, really stable, and the reason it's stable is because it's very happy because it's shared. The oxygen is sharing these two electrons, which make 8 electrons in the outer orbit. And when you have 8 electrons in the outer orbit, no matter how they get there, they're really happy. They like it. They're very happy. They don't like to separate. They don't like to. It's just perfect. It's the way they like to be. So here's a couple other examples. Okay, so when we look at sodium and chlorine, so when you look at sodium, the sodium and chlorine sitting in a tree. K-I-S-S-I-N-G. First comes love, then comes marriage, then comes salt. Right. So we got sodium. You'll notice, okay, this is a chart that has its outer orbits. The whole Kool-Aid thing's taking me back to my elementary school days, I think. So you've got sodium here. Look at the outer orbits, okay? So N equals the orbit shell, all right? So N1. And so you look at its outer orbit. Sodium has 3 orbits, and in the outer orbit, it's got 1 electron in it, right here, okay? Then when you look at chlorine, down here, chlorine, and it also has 3 shells, 3 orbits, and in its outer orbit is 7. So when you take the sodium that has 1 and you combine it with chlorine, which has 7, then you form salt. And they have 8 electrons in their outer orbit, and they're really, really, really happy. They like it now. So that's why salt's so stable. Salt really likes to stay together as well because they have those 8 electrons in their outer orbit. Okay, so basically they form when you take those outer orbit electrons, when they form 8, when they can form 8. So an ion, this is a definition you may need to know, and we're going to explain what this is. An ion is an electrically charged atom or group of atoms. Okay? Yippee! You are going to need to know that definition. An ion is an electrically charged atom or group of atoms. So let's explain how ions occur. So when you take something like salt, sodium chloride, right, and they're happy because they have 8 electrons in that outer orbit. They're all happy. When you take that and you put them in a solution, then they separate. So the atoms separate from the compound. Okay. But they don't like to give up their happy 8 electrons in the outer shell. So basically what you have here, all right, is you have chlorine. Chlorine is like the good-looking rich lady. You know, she's the one with all the furniture and the house and all that stuff. And then you got sodium. And sodium meets chlorine at a bar, and they're hanging out, and they get to talking, and sodium's got a really, really nice TV. And so, you know, they fall in love, and they move in together, and they're all happy, and the sodium brings his television, and he gets to use all the furniture and the dishes and live in the chlorine's house, and everything's all happy and good and everything until they get put in solution, and suddenly they argue, and the chlorine gets mad one night and kicks the sodium out, and the chlorine says, "You get out of here, you get out of here, but you're not taking your TV, you're leaving your TV here." And so the sodium has to leave without his TV, and he's out there without a television now, and the chlorine now has all the furniture and the dishes and the nice TV, and so she's a happy. She's still got basically those 8 electrons in her outer orbit, and the sodium's out there without it. So here we have. Okay, so here if you look at the atoms, right? Here's the television, the 1 electron in its outer orbit, and And then chlorine has all the TVs and all the furniture and the dishes and all that stuff right here, right? When they move in together, they share them. But then when the chlorine kicks the sodium out, notice he doesn't have that outer orbit anymore. He had to leave his TV here. So now this is the TV right here, and this is all the furniture. I don't know why I always feel depressed after I teach one of these chemistry classes. But atoms separate, but they don't like to give up the 8 electrons in the outer shell. And by the way, just in case you're curious, most ions with positive charges keep the same name as their corresponding atoms, but most ions have, but most ions that have the ending "ide" added to the root of the word for the corresponding element. So, all right. So, like if you're a negatively charged ion, so if you have a negatively charged ion, then you add "ide" to it. So if it's chlorine and it becomes a negatively charged ion like chloride, then you add the "ide" to it. So you know that if something is, because you've heard the term bromine. Bromine, when it's ionized, it becomes bromide. Okay? Chlorine, when it's ionized, becomes chloride. And fluorine becomes fluoride. So negatively charged ions, when they become ionized, you add the "ide" to it. So, all right, so valence. Valence of an element in an ionic compound is equal to the number of electrons that an element loses or gains during the formation of a compound. Basically what that means in English is that, all right, so we take the sodium and the chlorine. All right, so the sodium atom had the same number of protons and electrons, 11 each, when it gave the 1 from its outer orbit to the chlorine atom, now chloride ion. It still had 11 protons, but now since it had to leave when it separated and became an ion, it had to leave its extra electron over with the chlorine. It now only has 10 electrons. Since protons carry a positive charge, the sodium ion now has a positive valence of 1, so a plus 1. And so if we had 11 protons and 11 electrons before, but we had to give up one of our electrons to the chlorine. So now we've got 1 less electron than we have protons. And so since there's more protons now, that carries a positive charge. It's the exact opposite with the chlorine. Okay, the chlorine atom had 17 protons and 17 electrons. Now, thanks to the generosity of the sodium, it has 18 electrons, but still 17 protons. Since electrons carry negative charge, the chloride ion has a negative valence of 1. Okay, so basically, if you took any ion, if it had 3 more electrons than protons, you would have a negative valence of 3, minus 3. If you had 3 more protons than you have electrons, then you would have a plus 3 valence. All right, so let's just go through some review questions here. So the "ide" means it's positive. No. A negatively charged, Jen's asking, so the "ide" means it's positive. No, usually if you see "ide" on an ion, then it's going to be a negatively charged ion. So "ide" means that it's going to be negatively charged. So anytime you see chloride or fluoride or bromide, that's a negatively charged ion. So you only add "ide" to the negatively charged ions. The positively charged stay the same. Okay, the names of them stay the same. All right, so an electrically charged atom or group of atoms is called an ion. If you were to take a large piece of coal and break it into smaller pieces, the resulting change would be a. If you guys want to do the chat room, we have time here. Let's see if you guys can guess. So just chat in the answers here. Just type in the answers, and we'll go through and kind of do a little review here since we have a little time on this one. So if you were to take a large piece of coal and break it into smaller pieces, the resulting change would be what kind of change? Good, Bob. Physical, very good. Good, Todd. Okay, so yeah, that would be a physical change. If you set fire to one of your competitors' business, no, I'm sorry, wrong. Yes, if you set fire to one of these pieces and they turn to ashes, this is called a chemical change. Very good. Okay, yeah. If you're going to chat, let's, unless you don't want anybody to see it, click it over to everyone. So when you're chatting, switch it over to send to everyone, unless you want it to be a private chat, somebody specifically, because we record the chats and that helps. Okay, so the molecular weight of ordinary water is, you know, this came from the book if you read the books, but who cares? 18 grams per mole. You guys didn't know that, we didn't cover it, and because nobody's ever going to ask you that. I don't even know why they review questions in the book. Protons and neutrons are found in what part of the atom? This one's a relevant one. This is something you may need to know. Protons and neutrons are found in what part of the atom? Nucleus. Good. Good. Yep. Nucleus. One prevalent theory is that all elemental atoms seek to achieve the blank type of structure. I don't know if I used this word or not when we were describing it, so I'm going to go on and give it to you. It is the inert. Inert means that it's not moving around. So basically, if when the atoms are, you know, when they ionize, when they are, or when they form compounds, and so the sodium, they're moving around. They're looking. When things are moving around in the water, they're all looking for things that can give them that 8 electrons in their outer orbit. That's when they're happiest. So sodium is moving around looking for something with 7 electrons in its outer orbit. Just so happens that chlorine is one of those. So once they find it, then they reach the inert status. They stay. They become stable. And they like it when they have that 8 electrons in their outer orbit. By the way, let me go back. I want to go back. Let's show you guys that. I forgot to mention that. On this guy here, we were talking about the you know, in terms of stability on the compounds. Notice here on the inert gases, this is where I should have mentioned this. The inert gases, neon, argon, krypton, which I think is way cool that there's actually a substance actually called krypton. The geek in me, I think. And xenon, I always think of Princess Warrior for some reason there, but if you look here, except for helium, all of the inert gases have 8 electrons in their outer orbits, so they don't form compounds with anything else very easily. They're already really, really stable by themselves. That's exactly where they like to be. Okay, so all of these guys, the halogens, are looking for something with 1 electron in its outer orbit. The alkaline earth metals are looking for something with 6 electrons in their outer orbit, and the alkali metals are looking for something with 7 electrons in their outer orbit. Okay, and so they can all reach what these guys, the inert gases, have, that inert status. All right, so let's go back to the questions. Okay, yeah, right. Nucleus, yes. Okay, one prevalent theory is that they're inert. They're all seeking that inert status. Okay, so the molecule is a substance which cannot be decomposed chemically into a simpler substance. True or false? A molecule is a substance which cannot be decomposed chemically into a simpler substance. True or false? Free to jump in and guess. 50-50 chance. Promise not to make fun of you too much if you get it wrong. It is false, actually. Sorry, the one person who guessed. And it's an atom that can't be broken, that cannot be decomposed chemically into a simpler substance. A molecule is actually 2 or more atoms of 1 or more elements. So a molecule can be broken down into atoms. So you guys are never going to want to answer questions again. All right, scientists claim there are more than 25 basic particles, such as the electron, proton, and neutron in the universe. It comes straight from the book. We didn't really talk about it, but the answer is true. I'll go on and give that one to you. You're probably not going to see that question on the exam. It's, you know, like I said, who cares? An electron can be said to possess an electrical charge of -1. True or false? An electron, good. Yes, true. That is true. An electron carries a negative charge. Good. The number of protons in the nucleus is equal to the neutrons outside of the nucleus. True or false? That's right. It is absolutely false because the neutrons exist in the nucleus. They're inside the nucleus with the protons. Paper, nylon, egg yolk, turbid water, and gasoline are all mixtures. True or false? That's true. They're all mixtures. The book talks about that. And it goes into a little bit more detail than I did. The number of electrons surrounding the nucleus of an atom have little effect on its weight. True or false? The number of electrons surrounding the nucleus of an atom have little effect on its weight. It's actually true. The only thing that affects the weight of an atom are the neutrons. Neutrons are the only thing that affect the weight. Electrons have very little effect on its weight. Electrons affect the chemical properties, but they have very little impact on its weight. The evaporation of a mothball is an example of a chemical change. True or false? This is actually a physical change. The evaporation, remember, it's just like, so when you take that, anytime, basically the mothball is just simply turning to vapor. So that is not a chemical change. All you're doing is it's going from a solid form to a vapor form. So the evaporation of a mothball is an example of a physical change. It would be just like water. And I know that one gets a little confusing sometimes, but when you think about it, you've got the same molecules. You're not making new molecules. The valence of an element is expressed as a small whole number and is designated as a plus or a minus. We didn't really talk about that too much. The book does a little bit more, but that is true. And that was pretty much common sense. I mean, you run across that all the time when it comes to iron. You know, you see Fe++ or Fe++++, or, you know, and so I mean that one's pretty simple to figure out. The weight of an electron is extremely light. Actually, its specific weight is blah, 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 blah. This really long one with a bunch of zeros and a 9 on it. Or C, who cares? The answer is, seriously, who cares? I think it's all of the above, actually. You're not going to get asked that. The book, that was a question in the book, but the reason I added these up here is because a lot of people, and I did kind of want to point this out just to make sure you understand, that a lot of people use the questions in the book, the review questions in the Water Treatment Fundamentals book, as preparation for this test. And some of the questions in that Water Treatment Fundamentals book are just so out there. And I think they're really intimidating. I think people read those and they're like, oh my God, I'm going to do horrible in this test. And they tend to focus so much on stuff like this, on the chemistry and trying to learn that stuff, but they really miss the important stuff, which is, you know, how and why this stuff actually works. That's one of the things I tried to do in this course. So, and that's the purpose of these review questions, let you know that some of the questions in there, they're not that big a deal. Don't stress over them, okay? Who cares? And here's basically your rule of thumb. If you're never going to use it, you know, and you can't think of a time that it would ever be relevant, don't worry about it. This test does a pretty good job of testing, of demonstrating the practical application of the water treatment industry. So, and you know what? 0, 0, 0, 0, lots of zeros and a 9, it does nothing for us in this industry. Okay, Some of the following statements are true of compounds. Which are they? They have definite freezing and boiling points, can be separated into constituents by purely physical means, are heterogeneous, that is, relative amounts of constituents may vary within the sample, usually retain the properties of their constituents, have compositions that may be varied over a limited range. Which ones of these are true of compounds? Any idea? A definitely is true. The answer is actually only A. The compounds have three characteristics they have three characteristics. So they definitely have freezing and boiling point. So they have a definite freezing and boiling point. They also have different characteristics of their makeup constituents. So if you think salt, the compound salt looks completely different than sodium by itself or chlorine by itself. So it has a completely different characteristic than its makeup constituents. Okay, so and then lastly, it is homogeneous, not heterogeneous. So those are the three characteristics. So the only one of these that is accurate is A. They have definite freezing and boiling points. Atoms with the same atomic number but with different atomic weight due to varying numbers of neutrons in their nuclei are called isotopes. Well, I'm going to give, we didn't talk about that. That's in the book. You read the book and you might have known that. Many ions are electrically charged. A, groups of atoms, B, protons, C, electrons. So many ions are electrically charged. What do you guys think? A, B, or C? The answer is A, groups of atoms. Many ions are electrically charged groups of atoms. Okay, blank, determine chemical properties. Protons, neutrons, or electrons. Which one determines chemical properties? C. Very good, Bob. Very good. Okay, blank simply adds mass. Protons, electrons, neutrons. Which one adds mass? Just adds mass. The answer is C. Neutrons simply add mass. That's all they do. Neutrons are neutral. They do not contribute to an electrical charge, positive or negative. So the answer is C. That neutrons simply add mass. You may see that question again. You will need to know a little bit about what carries a positive and negative charges and what neutrons do. That's it. So next week we will delve a little deeper into chemistry again. I do recommend that you read the chapters, all the chapters, but it does help to kind of understand some of this stuff. I don't know if those of you have read the chapters before you've taken a webinar, but it does kind of help. The book goes into a little more detail, a lot more detail. If it makes your head hurt, don't stress over it though. Okay, like I said, only 12% of the exam is chemistry. But when we start getting into things like ion exchange and how resin works and how stuff is oxidized, that's where the chemistry really becomes relevant. Do want to take just a second here and invite everybody to our Thursday morning MV Pro call. 8:30 is Thursday morning. It's a half hour. We have sales professionals from all over the country that log on and talk about, we don't talk product and we don't talk company. We do talk industry and sales. Right now we're working our way through how to win friends and influence people. Dale Carnegie, it's just an excellent discussions. But as always, anybody has any questions, you're more than welcome to give me a call. The sample quiz questions that are more relevant to what you'll find on the exam are on our website. Feel free to log on and take those. And if you have any questions, either give Jen or myself a call and or shoot us an email. And if I don't talk to you beforehand, I will talk to you next week. Thanks, everybody. Have a great rest of your week.